everybody, this is Harbin. Welcome to Video Notes 1.1. Let's get started. Here are the things you're supposed to learn from today's video notes. Please also read sections and take notes on Chapter 11, sections 1 through 6, those pages. All right, so grab a carrot. Let's get started. So models. Models are ideas or representations that scientists use to explain patterns we observe in the world. We love models. So, what makes a model good is whether it's acceptable or not based on how well it explains and predicts data and how consistent it is with what we already know about the world. So, we think matter is made of atoms. So, we can look at some early models of the atom. At first, when this idea was proposed, it was proposed that atoms were just solid spheres, okay? And that those solid spheres of one kind of element were different than the spheres of another kind of element, okay? And so on for all the elements they knew about. Then, with some really fancy experiments, another model of the atom was proposed that had these negative parts to it called electrons, okay? One experiment called the cathode ray experiment, analyzed and done by J.J. Thomson, showed the existence of these charged particles that were later called electrons and negatively charged. But still, that model didn't explain all of matter's properties. This model of the atom was proposed after an experiment called the gold foil experiment, and a small, dense, positively charged nucleus was also proposed. So these are the models, early models of the atom. This one is that atoms are made up of spheres. This one is that atoms have negative charge in them. Negative charge. But in order to have negative charge, there has to be positive charge as well. So there's kind of a dough. And after that negative charge was discovered, the dough had to be the positive and then the negatively charged particle. So we had to change our model. And then the nucleus was discovered. Nucleus was detected, I should say. And so we had to change our model again. Niels Bohr came up with a model of the atom that had that nucleus with protons and neutrons in it, but described a little bit more detail about where the electrons were. He proposed that electrons were in energy levels outside the nucleus. One way he did this was he used an experiment called the bright line spectrum. Okay, he found out that atoms would produce different spectra if they were different atoms. So the way he explained that was to say that every atom has different electrons with different energies, and those electrons can jump to higher energy levels if energy is added, but then those electrons go back down to lower energy levels and release energy at different frequencies, and the pattern of the different frequencies depended on the quantized electrons in the atom. And each different atom of an element, each element had a different pattern for that. Okay, we sometimes call this the planetary model because then there was the idea that the nucleus with the protons and neutrons was in the centralized area, and that the electrons orbited around that nucleus. Okay, that's almost right. Right, we do have the energy levels are right. They can be explained by the quantum, but Bohr's ideas only work to explain very well the hydrogen atom and anything else. If there's more than one electron in an atom, like any other element that we have, that model didn't work. Okay? So, in order to understand a little bit more about how the light helped us figure out atoms, we need to know what light is. So there's this thing called the electromagnetic spectrum, and you can see right here that visible light is a small part of the entire electromagnetic spectrum. Here's all the other kinds of waves that are on that spectrum. Okay, so visible light waves are here, but we have radio waves, microwaves, visible, infrared, visible, and ultraviolet radiation, and X-rays and gamma rays. So all of those kind of waves are part of the electromagnetic spectrum. The difference between them is that some have long wavelengths and some have short wavelengths, and all others in between. So that means if you're standing in a spot watching these waves go by, the higher they, more often they go by, the higher the frequency, the shorter the wavelength. So these are high frequency, short wavelength, and these are low frequency, long wavelength. And you can see that visible light is somewhere in between. Okay? So just to give you a little more information about the electromagnetic spectrum, if you think about radio waves, the wavelength of a radio wave could be the size of a building. And then somewhere between radio and microwave, those wavelengths get smaller, maybe the size of humans, and smaller to honeybee size. And then you get to infrared. That's right before the visible spectrum. And those are even smaller. Visible light has wavelengths that are the size of tiny, tiny cell creatures. And then when you get to ultraviolet, X-ray, and gamma rays, you get to the size of molecules, atoms, and then the nuclei of atoms. So you can see that as the frequency increases, the wavelength decreases. And here's just to give you a relative idea of those wavelengths. Okay, so what that means is that some electromagnetic radiation is small enough, okay, has short enough wavelength to hit particles like atoms and molecules in DNA and knock electrons off of them. And so we call that ionizing radiation. Makes ions when interacting with matter. Okay? Because there's high frequency and high energy when there's more frequent waves, these waves have enough energy to knock electrons off of things. And so then you can get damaged DNA, you can break bonds with that ionizing energy. If you notice, the highest frequency or the electromagnetic radiation that can do that is some ultraviolet waves, X-rays, and gamma rays. Things like radio waves and microwaves aren't able to knock electrons off of things, so they're considered non-ionizing. Okay, they do cause things to heat up, though, but not from ion type, energy of ions. It's energy of motion that causes heat. So that's a little bit about electromagnetic spectrum. And so using all that kind of information, scientists were able to determine stuff about the atom. And now we have a current model of the atom called the quantum mechanical model. Quantum mechanical model. So taking all of those previous experiments and evidence and ideas about atoms and adding to them and changing them, we now believe still that there are protons and neutrons in the nucleus of an atom and that there are electrons and energy levels outside the atom, outside the nucleus. And those electrons occupy energy levels, but the energy levels don't look like rings. They look more like clouds of possible places to find electrons. Okay, so we call these things orbitals, right? And the wave model and the photon model of matter and light help to develop some probability and mathematical ideas about where these electrons are. Okay, we'll talk about where the electrons are a little more in the next unit, but hopefully you remember this, that atoms are made of protons in the nucleus, which are positive. They have a mass of 1 AMU, atomic mass unit. So, do they weigh 1? Sort of. Compared to other parts of the atoms, protons and neutrons have about the same mass. And so they get the label of an atomic mass unit. There is an actual mass for it. It's a really, really, really small number of grams. But since these have about the same mass, they called an atomic mass unit. So if you know the protons, you know the identity of an atom. You know the neutrons are in the nucleus, they have no charge, and they help to determine the mass and stability of an atom. And then there are electrons. Electrons are in the electron clouds outside the nucleus. They're negative. They have negligible mass, which means it doesn't matter much compared to 1 AMU. It's about 1/2000th. That's an estimate. I mean, that's a rounding of a proton or a neutron. But it does determine the charge of an overall substance, okay, because they're negative, and if electrons change, the charge of an atom changes, okay. So these neutral building blocks of elements, you should make sure you have it in your notes. Please label the nucleus in there. Okay, I want you to label these. Label it. I know it says it right there. Label the nucleus, the protons and neutrons and the electrons here. Okay, and if you notice, 1, 2, 3, 4, 5, 6 protons, 1, 2, 3, 4, 5, 6 electrons, and so atoms are neutral because their protons and electrons equal each other. All right, so to review, atoms are neutral. Yeah, we just said that. We have a model of the atom thanks to scientists who've done experiments and analyzed data and worked really hard to figure stuff out. The atomic number is the number of protons, and atoms are neutral, so protons equal electrons. You should be able to figure out how many protons, electrons, and neutrons there are in an atom. We'll keep practicing that. Light was a key to understanding the atom. Electromagnetic radiation has a spectrum of waves that all travel at the same speed, but some have more energy than others based on their frequency and wavelength. Longer wavelengths have low energy, and shorter wavelengths have high energy. Some electromagnetic radiation is ionizing, while other stuff is not. So, hey, look, it's little hamster again. So hopefully you look at the book too, which takes some more information, gives you some more information. That was fun. And here's what hopefully you learned. Peace out.